Welcome back once again. We were talking about the circuit analysis methods, mesh current method we already examined. Now we will be examining the node voltage method. So each method we need to introduce a new variable. So our new variable is going to be node voltage. Let's go inside. Circuit analysis by node voltage methods. New variable is node voltage. What is node voltage? Node voltage, the voltage measured between a node and reference node, is called that node voltage. So any node, there is a reference point. Reference node voltage is 0. So if there is an element when the circuit given to you, it has got ND nodes. One of them is reference, of which node voltage is equal to 0. For the other nodes, when I say the node voltage, is the voltage between this node and the ground. So it could be from time to time an element voltage if this element connected a ground and a node. But if the element is not connected to the ground, then an element voltage is not equal to a node voltage. So we're going to solve how we're going to write the element voltage in terms of node voltages later on. So assume that for each node there should be a voltage node, this is the one that we mentioned, such that each element's voltage can be calculated by these node voltages assigned to the element's terminals. So element terminals must be connected to nodes. So you know the node voltages, how you're going to calculate the element voltage itself. So come to this new frame now. It is explained in this frame. Here we are, there is an element A. This element is connected to node 1, of which node voltage is VD1. As you see here, VD1 is the voltage between that node and the reference, which is 0 volts. Node volt, of which node voltage is 0. And this second terminal connected to this A. Second terminal of this element A is connected to node 2. And node voltage of node 2 is this voltage. So node has got plus voltage reference, and the reference node has minus voltage reference. So according to passive sign convention, the current direction is going to be like that. For the other one, it's going to be like this. Now, question is, how are you going to write this element voltage in terms of the node voltages VD1, VD2? The other node voltages is not going to be seen for the voltage of this element A, because this element is connected to only these two nodes. So each element has got two terminals. Each terminal could be related with a node. Therefore, it's going to be there's going to be only two node voltages that we're going to use. So the rule is how to write the element voltage in terms of node voltages is easy. We're going to follow the Kirchhoff voltage law. Assume that there is a loop here, or you might call it a mesh as well. So in that loop, we can write the Kirchhoff voltage law equations. Let's write it. I have chosen a direction here for the loop. So direction of this loop current is the same according to passive sign convention. This A element's current reference from left to right according to passive sign convention. So which is the same direction of this mesh current. So VA has got plus in front of it. So if you consider this node voltage, assume that there is an element here of which voltage is VD2, that is node voltage. This element voltage VD2, this element current direction is this way, from up to down. Also the mesh current direction is the same way, so it's going to be plus sign, plus for VD2. And when you come VD1 current direction and the loop mesh current direction is the opposite to each other, so we're going to put a minus in front of VD1. equal to 0. This is the Kirchhoff voltage law equation for this mesh. So if you take this VA to the one side of the equation, VA is equal to VD1 minus VD2. So we can write a rule from that this example conclusion. It says the n element voltage VA is equal to the elements plus related terminal node voltage plus related node voltage, which is VD1, minus elements minus related node voltage VD2, which is this. VD1 minus VD2 is this element voltage. So the element there, you've got to have the element voltage reference of current or current reference in order to write this element voltage in terms of node voltages according to this rule. So this step is critical because once you know the node voltages, you can write the element voltages conclusion. So the next step, then we can introduce the new method now. Write the Kirchhoff independent Kirchhoff current law equations. Write the independent Kirchhoff current law equations. So independent ones, we know that reference node, we do not to write the Kirchhoff current law equations. If you forget that, ND minus 1 equations we are going to write for the nodes. One of them reference, that's why that's minus 1. So in these equations, what we are going to see, element currents, so any element currents that we are going to see in these equations. The next step, we are going to replace the element currents with the element voltages by using definition relation. It says substitute elements current for elements voltages by using elements definition relation. So if you consider the resistor, current is equal V over R. So if you use the definition relation, you can replace the current with the voltage of the resistor. So you could do that. You could also do this for the dependent sources, dependent voltage sources, but you cannot do it dependent current sources. I will explain the details later on. So in this case, if you do this, in general, consider the resistors only. Number of equation is going to be ND minus 1. It's not changing. Whatever the equation number here is the same as here. But since we replace the currents with the voltages, so the new unknowns in these equations are going to be the voltages rather than the currents that we see in step 1. In step 3, what we are going to do, in these equations we've got element voltages. We already made a rule on that frame saying that all the element voltages can be calculated in terms of node voltages. So we are going to replace all the voltages in step 2 with the node voltages. So if we do the replacement, the number of equations are going to be the same as the unknowns, which are node voltages. So from these equations we can find out all the node voltages. Once you found all node voltages, then you can find all the element voltages. Once you found the element voltages, you use definition relation and find all the element currents. Now in step 2, there are some cases that we've got to pay attention. What is this? In step 2, if an element current cannot be substituted for its voltage, then keep this element current as a new unknown. This could be currents of dependent voltage sources. That is IVS, independent voltage source current. This is current controlled current source current. And this is voltage controlled current source current. Dependent and independent current sources, currents cannot be replaced with the voltages of these elements. So we are going to keep those as soon as you see them. leave there in these equations. We cannot go any further, we cannot do any process on these variables. So we introduce new unknowns. So since a new unknown came in, addition to the node voltage equations, then an additional equation is needed to write. This equation is called supplementary equation. How we are going to write this supplementary equation? The definition relation of the new introduced current unknown, which could be any of these three elements, which is dependent and interdependent current sources. In this definition relation, all the variables should be transferred to the node voltages. So this a new variable became a new unknown. For this unknown, you're going to write an additional equation, we said. How we are going to write it? We are going to use this element's definition relations now. In the definition relations, of course, there could be some unwanted variables. We are going to transfer these unwanted variables to the wanted variables. How we are going to do it, you're going to see it in the example and understand it much better. Once the linear equation is solved, all the node voltages and new introduced unknowns are found. This solution is unique since the number of equations is equal to the number of unknowns. So at step 3, we found all the node voltages. Then next step, next level, you're going to find all the element voltages by using the node voltages. Use the definition relation, find all the elements currents. That is the final point for the analysis of a circuit. So let's examine an example. Here you are, there is a circuit here. In this circuit we've got 7 elements. Altogether we've got to write 14 equations if you're going to use the classical method to analyze this circuit. So we are saying we are not going to use node voltage method. We've got 4 nodes here, 1, 2, 3, 4. This one is ground. And we are going to do it step by step. The first step is write the Kirchhoff current law equations for these nodes. We've got 4 nodes. 4 node voltages means at the same time. So the first one, in this node we've got 2 elements connected, and the current references for these elements are these blue ones. Summation of those, both of them out of the node, so sign is positive, so equal to 0. So how to write these step by step? I will be giving for each step, explain just one equation how we are writing it. If you want to see step by step all the equations how they are written, follow this video given here. In this video you're going to see step by step how these equations are written. So for the first step I explained to you this first one. So the second step, we are going to replace the resistors. We are going to use the resistors definition relation and transfer the resistor currents with their voltage. In here that I2 is this 2 ohm resistor current. When you replace it with the voltage V2 over 2. 2 is the resistor's resistance. V2 is the resistor's voltage. So V2 over 2 is equal to I2. That is the usage of the definition relation of this resistor. So when you come to that I1 is the current of independent voltage source. I cannot replace this current with any voltage. Why is that? Because definition relation of this gives you V equal to 40, which is this definition relation. Here you are, V1 equal 40. What does this mean? This means by using the definition relation of this element, I cannot replace this element current with its voltage. As I did it in resistor, I can't do it for this one. So in this case, I am going to keep this independent voltage source current as it is, as shown here. It is there. It is also true for the node voltage connected this current controlled voltage source. This one. So let's come to this one. I cannot replace this current with the voltage of this element, because definition relation is given here. In this definition relation, this element current is not seen at all. So I cannot replace this current with anything else. So I'm going to keep it as it is. So what happened in step 2? I have got element voltages and two new unknowns introduced. The third step, I am going to replace all the voltages that I see in step 2 with the node voltages. It is easy because we already said how to find the element voltage in terms of node voltages. It is explained here. So you could use this rule and transfer all these voltages in step 2 to the node voltages. That's step 3. So the last case, step 3, tells us for ND node voltages that we have here, VD1, VD2, VD3, VD4, and we've got two new unknowns, I1 and ICCVS. So I've got to write two supplementary equations. So as I said already, we couldn't use the definition relation of those elements in order to transfer these currents to the voltages. Therefore, we will be using these elements' definition relations for finding the supplementary equations. Here it is. Let's start from the dependent source. So definition relation of the dependent source is this. So this is not given to you in practice. You're going to write your own. How you're going to write it your own is easy. I am saying this is a diamond, so that means dependent source, and this is a dependent voltage source. Why it is that? Because voltage reference is given. So current controlled voltage source voltage is equal to 8 times IC. That IC is another element current, which is this resistor current. So this is the definition relation of this element written here. The next step, these two variables V, CC, VS and IC are the variables, not the unknowns in my equation. Not among the unknowns in my equations, not in these unknowns. So I am going to transfer these two variables with these unknowns. It is easy. How? That is an element voltage. I know that each element voltage can be written in terms of node voltages, so we can write this. Let's come to the current. For the current, this current is an element current. This is a resistor current, which is 5 ohm resistor current. So I'm going to transfer this resistor current to resistor voltage. So this is now resistor voltage VD2 minus VD3 is the resistor voltage in terms of the node voltages. So resistor voltage divided by 5 gives you the resistor current. So that is the IC. What I have in this equation are the node voltages only. This is the equation that I am looking for, and this equation is the supplementary equation 1. So this supplementary equation and another supplementary equation I've got to write for this independent voltage source. So already said, this is the definition relation of the independent voltage source. So I am going to transfer this to a supplementary equation. How? Since this is a voltage of an element voltage could be written in terms of the node voltages. So that means V1, since the other terminal is connected to the ground, that 40 is equal VD1. So this is the second supplementary equations that I add on. So if you consider these 4 equations plus this one, supplementary 1 and this supplementary 2, we've got 6 equations and 6 unknown. We can calculate the node voltages from here. Once you found the node voltages, then you can find all the element voltages. Once you found all the element voltages, you can find the element currents by using the definition relations. So that is it. It says also it is possible direct to write these third step mesh current methods equations, not node voltage equations it should have been. You can write a rule for that. So that is the end of this video then. Let's stop here.